Thank you very much for attending this session. This is session 2 of main experimental facility, modeling, and technology. The remaining equipment that we have at HydraFACT is the objective of this presentation. So one of these equipment is what we call it commercial name HydraCHEK. In fact, this will determine hydrate safety margin. What is hydrate safety margin? Hydrate safety margin is the hydrate phase boundary that we need composition of hydrocarbon and composition of water. Now, hydrocarbon composition doesn't change much with time. But the water composition, the aqueous phase composition, can change in very short notice. For example, injecting too much inhibitor or too little inhibitor, or breakthrough of the formation water that can change the property of the aqueous phase very suddenly. So this is hydrate phase boundary. And this is, we assume, the pipeline condition. The fluid that comes from reservoir is warm and high pressure, and as it moves to downstream condition, it can go various conditions of pressure and temperature. For example, here I have simulated condition at Ommelanga, that is a gas condensate reservoir in Norway, at deep water and then shallow water. Shallow water temperature goes up. So by hydrate safety margin, I mean the difference between these two curves. Because ideally, you don't want the pipeline condition to be inside hydrate stability zone, because hydrate can form. But too much away means that you need to use too much chemical. So something like this. If the hydrate, this is, for example, this is pipeline condition. If the hydrate phase boundary is here, there is a risk of hydrate formation. So we need to either move the pipeline condition to the right or move hydrate phase boundary to the left. Moving pipeline condition to the right, meaning that you need to provide heat. And that is normally very expensive. So the other option is to shift the hydrate phase boundary to the left. For that, we need to inject inhibitor. So for example, we can inject inhibitor, shift the hydrate phase boundary to this yellow line. Now we are outside hydrate stability zone, but very close. So you might decide have the safety margin. This is what industry uses, at least in the design stage. But you can imagine at the design stage, First of all, reservoir pressure is much higher. Secondly, those people do not want to take any risk, so they propose higher inhibitor injection. And for various reasons, normally they inject more than what is required. So if it is here, it's ideal. But most cases, we are here. Especially even in the beginning, if it's not there, with time, reservoir pressure will drop and the risk of hydrate is less. But most companies will follow the original inhibitor injection. So most of the company inject too much. So, for example, if the amount of inhibitor we are injecting push our hydrate stability zone to this point, we are wasting inhibitor. We are injecting too much inhibitor. It is expensive and also it can damage the environment. So you can see that if you know the composition of aqueous phase, we can design the safety margin. If you are here, we can reduce the amount of inhibitor. If you are here, you can increase the amount of inhibitor. So what we need, as I said, the composition of hydrocarbon doesn't change normally at short period. So it is the composition of water. So you might say, well, we take a sample. Yes, we can take a sample and send it to the lab. But it takes time. It can take 12 hours to 24 hours. But that time, the condition has changed. So we need something that can measure the amount of salt and inhibitor in water quickly. That is the purpose of this device. This device measures three properties: conductivity of the aqueous phase, velocity of sound in the aqueous phase, and temperature, because with temperature, this parameter will change. So in effect, we have two independent parameters. Although we measure three parameters, but two of them are independent. Because velocity and conductivity are a function of temperature. So we have two known and we can find two unknowns. The unknowns are salt and chemical inhibitor. So with this device, within 5 seconds, we can determine the amount of salt and chemical inhibitor, like MEG, TEG, methanol, ethanol, or KHI, we can determine within 5 seconds. So almost real time. And then by knowing the amount of inhibitor, we can plot the hydrate phase boundary and see that if we are outside or inside, how much we are outside, how much we are inside. Then we can adjust the amount of inhibitor considering real reservoir condition, pipeline condition, and temperature of the pipeline. So we can optimize the amount of inhibitor. And we have many cases in this. So this is lab-based that we need to put it in the lab. The reason we have to put it in the lab because we can have this is not proven for flame. So there are electrical connection here. So it had to be in the lab. So it's not ATICS approved, Zone 1 approved. So this is lab-based HydraCHEK. But this is online HydraCHEK. This one is ATICS approved. It can take sample at high pressure, 250 bar, and then reduce the pressure to atmospheric, increase temperature to get rid of all emulsion, and then decrease the temperature within 15 to 25, and then the measured conductivity and velocity and amount of inhibitor, and then dump the sample into the pipeline or a storage tank, and then with distilled water clean the cell and take another sample. This process for each sample will take 20 minutes to half an hour. But obviously the operator decides how often to take sample. So this they have been commercialized and they are used by industry. And with this HydraCHEK, we play a major role in winning the Queen's Anniversary Award for HydraFACT for Heriot-Watt University. Because with this device, Total was able to extend the life of the reservoir by 5 years and reduce the amount of inhibitor from 28% to 0%, which was recognized by the judges in the Queen Anniversary Award and also Institute of Chemical Engineering of UK. The other device that we have developed within my research group at Heriot-Watt University and commercialized by HydraFACT is HydraSENS. HydraSENS is a device for detecting early signs of hydrate formation. As you see in this figure, This figure shows the pressure and temperature of hydrate formation for different pure gases. The bottom one is H2S. H2S has a lot of tendency to form hydrate. This one, the black one, is IC4, isobutane. This one is propane. This one is ethane. This one is CO2. This one is methane. And this one is nitrogen. You see that different gases have different attraction to form hydrate. And you see that some gases have a lot of attraction, some gases do not have a lot of tendency to form hydrate. For example, here nitrogen doesn't have any tendency, very little tendency to form hydrate. And compared to IC4 and propane, IC4 like to form hydrate better than propane. And considering methane, you see that a lot more. So when hydrates form, some components have higher tendency to form hydrate. So when hydrates form, you expect to have more IC4 and propane in the gas trap in hydrate compared to methane. So you see that the composition of the gas trapped in the hydrate is different from composition of the gas in the gas phase. So if we start with 50% of methane and 50% of IC4, when you form hydrate, you might have 75% IC4 compared to 25% methane. So you see that hydrate formation will deplete the gas phase from heavy components. So when hydrates form, the amount of, for a structure 2 obviously, for a structure 1 different gases, the amount of IC4 and propane in the gas phase is reduced because it goes to the hydrate phase. And gas phase is the fastest moving phase in the pipeline. But hydrate has similar density than water, so it will remain in the water phase. So first, you see, if you sample the gas phase, you see a reduction in IC4 and propane compared to methane. So you have more methane than original gas. To magnify this, we can look at the ratio. So if hydrate starts to form, this ratio will increase. And this ratio will increase. And when hydrate melt, this ratio will drop. Because when it starts melting, you would more IC4 come to the gas phase. This is a real case. Total in France, they have a wet gas reservoir, and they were originally they were using methanol, but because water cut increases and methanol is no longer economical, they use anti-agromanant. But together with using anti-agromanant, they put a online GC analysis. And they saw this figure. They were part of the project. So we interpret this result, and here it shows that hydrate is forming, here is melting, here is forming, here is melting. So why it's melting and forming, we'll notice that is concentration of day and night. Night, temperature drop, hydrate forms. Day, temperature increases, hydrate melts. So they were injecting anti-agromanant, so therefore we were able to see that. And we noticed that during the year, only 10 days, the temperature was low enough to form hydrate. So in effect, they needed only anti-agromanant for 10 days. So here, this is the device we have created that automatically takes sample, and then depending what the outcome of the sample is, then warn if hydrate is formed. And because the change in composition will be first sensed in the gas phase, and gas phase, the fastest moving phase. So it is signs of hydrate formation. And also, we can also detect where hydrate is formed. You might say, how? Because there is a slip velocity difference between gas phase and water phase. Hydrate density is very close to water density. So hydrate will come with a water phase. Imagine the speed of the gas, its velocity of gas phase is 15 meters per second. Velocity of water phase, aqueous phase, is 5 meters per second. So a slip velocity is 10 meters per second. 15 minus 5. So at time 0, when we see the sign of hydrate formation in the gas phase, and then we take, whether we take action or not, but then we see the water coming in. Water, because it has hydrate, comes to separator and depressurization vessel, degassing vessel. We can monitor the gas composition that's coming from the gassing separator, because you need to remove the gas, then you want to do treatment of water, or you want to inject water, whatever you want to do, but you need to remove the gas. And we see there signs of hydrate formation, that from the gas release from hydrate, we see more IC4. We see more propane and also more gas because hydrate can store a lot of gas. If we time these, for example, we put a time 0 when we see sign of hydrate formation in the gas phase, and then, for example, in 1000 seconds, we see hydrate formation, sign of hydrate formation from the gas release from hydrate. We can say that hydrate is forming in 10 kilometers away because the sleep velocity was 10 meters per second. And we saw sign of hydrate formation after 1000 seconds. So the hydrate is forming 10 kilometers away. So we can use this to design how we are going to get rid of hydrate. If we are close, hydrate formation is close to the point that we can inject inhibitor, we can inject inhibitor. If it is too far from injection of inhibitor, we might decide to reduce the pipeline pressure. Not just assuming, but obviously what we do, we normally recommend to measure the viscosity of hydrate slurry. Normally up to 10 to 20% hydrate in the water phase will not result in blockage, but needs to be tested. We can also use this device. For example, we have a blockage. We don't know what the blockage is. And we have used this device for a blockage in the Middle East. And then from depressurization, we can say that is the gas is coming from hydrate or not hydrate. In this case, we were able to detect that the gas is not from hydrate and it is from wax. So this is another device that we have. Another two patents that we have at HydraFACT and we are commercializing it, which help with NOV, is kinetic hydrate inhibitor removal, recovery, and reuse. Kinetic hydrate inhibitor are among the low dosage hydrate inhibitor. The amount of this chemical normally is between 1 to 5% of the aqueous phase. So very little compared to thermodynamic inhibitor. Thermodynamic inhibitor, you need 30 up to 50%. So has a great saving with respect to, not with respect to price because they are expensive. For example, you can buy methanol 20 cents per liter, glycol 1.2 cents, $2 per liter. So for this reason, glycol is normally regenerated because they're expensive. And methanol is not preferred because it will poison the catalyst and also water treatment facilities. And also the other important point, as we need a lot of thermodynamic inhibitor, we need to think about logistic and also storage. So a lot of offshore facilities, they have to have a piggyback to deliver thermodynamic inhibitor because the amount is too much. Otherwise, they can use kinetic hydrogen because we have two limitations in offshore rig. One is the space footprint, and the other one is weight. So offshore rig, normally they use kinetic hydrogen. Now we have done a lot of studies on kinetic hydrate inhibitor, and we noticed that they have various regions. So if this is hydrate 5-phase boundary, we notice that for some inhibitor, PV cap inhibitor, we have a complete inhibition region. And then a slow growth, very slow, and then slow. And this is fast formation of hydrate. So, and interesting, this is a slow dissociation region. I'm going to have a webinar on kinetic hydrate inhibitor. But we now know that for what system, which inhibitor we can promote. So each inhibitor has a fingerprint. Together with the type of gas, we can say this inhibitor is better for this one. So now we expect the application of kinetic hydrate inhibitor will increase. But they are expensive, and also they are not environmentally friendly. So we developed a technique to extract the inhibitor from produced water, remove it, and use it again. So it not only solves the problem with cost and environment, but also it provides an opportunity to use chemical inhibitor, kinetic hydrate inhibitor with MEG. MEG is very popular, but the MEG regeneration or reclamation unit, they are very expensive. Capital cost is very expensive. And as I mentioned before, with concentration of MEG in produced water could be up to 50% and even more. So when water cut increases, we need more MEG, and that may be a problem. We also found that kinetic hydrate inhibitor can replace 20 to 40% MEG. 1% kinetic hydrate inhibitor can replace 20 to 40% MEG. So is an ideal condition to mix KHI with MEG. And you might say, why they haven't done it before? The reason is that water containing MEG will go to regeneration unit. And temperature in MEG regeneration unit can be 160 degrees. And KHI are polymer that can come out of solution at 40 degrees. So we cannot send the water containing KHI to MEG regeneration unit because all come out and block everything and it will be in a mess. So ideally, we want to separate KHI. And this pattern, the two patterns, are for separation of KHI, recovery and use. So, produce water, first, we add a fatty acid or fatty alcohol to separate the polymer and then send the remaining water to MEG regeneration unit. Now it doesn't have any polymer. And regeneration lean mean MEG is result of this MEG regeneration. So that loop create lean MEG. And then we have another loop to recover KHI, the polymer, and use it again. So we have two loops that can, for example, 60% MEG to less than 40%. So it has financial benefit and also environmental. So this is another service that we can provide. The last one is our HydraFLASH. HydraFLASH is our software. And it is compatible with Olga. And I will claim is the most accurate water, hydrocarbon, and solid software. The reason it is the most accurate one, because as you probably know, software work on experimental data. Reliability of software is what experimental data has been used for development. Obviously, it is important with thermodynamic model we are using the mixing rule and the rest, but software or experimental data, because its equation of state is not exact solution. It is semi-empirical. Empirical means that it needs experimental. So reliability of a software depends on the experimental data used in tuning them. We are the only company that is developing software and we have access to experimental. Our access on experimental data is project we do, and also the equipment that we have, experimental equipment that we have in the lab. So anywhere we have question, we can generate our data. Most of this software, experimental data, we can't publish. And we don't want to publish anywhere. So because the companies, they have paid for it, and it is their property. It's not our property, but we can use it for improving our software. And it has been many comparative studies, and is the most accurate one. So here you see different flash calculation: pressure, temperature, pressure enthalpy, temperature enthalpy, volume temperature, pressure entropy, and then temperature entropy. This is hydrate calculation. Amount of inhibitor we require, how much hydrate will form, and the KHI, effect of KHI on hydrate stability. And this is asphaltene, onset asphalt, amount of asphaltene, precipitation curve of asphaltene. This is wax, wax stability, wax control, EOS tuning, experimental data, PVT data we can use and tune, and then phase envelope, bubble point, pressure, temperature, dew point, pressure, temperature. Database, we have more than 20,000 database in our database. Mixing fluid, Volga tap file, freezing point, CO2, phase boundary. And then here is creating databases and importing, result, and complete setup here. And we provide 30-day free trial, and then you can try and see that if the software is useful for you or not. So these are some more pump that we have at HydraFACT, up to 10,000, 250 cc, and flow rate very small to 80. So it's 0.0001 cc per minute. This is a GC. This is a coefficient measuring the amount of water in hydrocarbon. This is hydrometer measuring the amount of water in the gas phase. So this is water phase, water content measurement. This is gas phase, water content measurement. We also have a mini fluid loop, mainly for wax studies. Look at how much wax we deposit in a fluid loop. We also have access to micromodel. It's a high pressure micromodel up to 6,000 psi. We can see wax formation, hydrate formation, asphaltene formation. Here you can see hydrate formation. And here as well, hydrate formation. This is a new setup, not a new, but it's a novel setup that we can measure solid deposition on the surface. We use this device for different coating, pipeline coating, internal pipeline coating, and effect on the wax and scale deposition. So there are 10 pieces of the metal. They are part of this circular in the middle, and this is a bottom ring. This is the top ring, and they are in a way that they keep the sample ring attached to the wall. And then this is a mixer. Torque, you can measure the torque in this mixer. And these are the blades. And then here, the temperature controlling system. We can increase or decrease temperature. And this can go to up to 6,000 psi and can measure the amount of wax deposition, aspartame deposition, or the scale deposition. Here we can use different paint to see the effect of paint on the deposition tendency, and we can create different shear rate as well. This is our office in Edinburgh, and our contact details are here. In this list, I mentioned the main experimental equipment. What we do with our experimental equipment is that we make it, we can modify it because we build them ourselves. We normally don't buy, except pumps and GC, we don't buy anything from outside, we build it ourselves. And that's why we have the ability to change the experimental equipment based on the demand or requirement. That's it. Thank you very much for your attention.